All right, this is CS50, and this is the start of week 4, and this is one of the slowest possible sorting algorithms. Which one was it that we just watched there? So that was bubble sort in order big O of n squared plus some. And indeed, we are not the only ones in this world who seem to know what bubble sort is or its running time. Indeed, this was an interview with Eric Schmidt of Google and former Senator Barack Obama just a few years ago.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president, and you're going through the rigors now. It's also hard to get a job at Google. We have questions, and we ask our candidates questions, and this one is from Larry Schwimmer. Okay. What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay.
All right. So last week, recall, we took a break from code, at least for a day, and started focusing on some higher level ideas and problem solving more generally in the context of searching and sorting. And we introduced something that we didn't slap this name on last week, but asymptotic notation, the big O, the big omega, and sometimes the big theta notation. And these were simply ways of describing the running time of algorithms, how much time it takes for an algorithm to run. And you may recall that we talked about the running time in terms of the size of the input, which we generally call n, whatever the problem may be, where n is the number of people in the room, the number of pages in a phone book. And we started to write things out like big O of n squared, or big O of n, or big O of n log n. And even when the math didn't quite work out so perfectly and it was n squared minus n over 2 or something like that, we would instead just throw away some of the lower order terms. And the motivation there is that we really want a sort of objective way of evaluating the performance of programs or the performance of algorithms that at the end of the day has nothing to do, for instance, with the speed of your computer today. For instance, if you implement bubble sort or you implement merge sort or selection sort on today's computer, a 2 gigahertz computer, and you run it and it takes some number of seconds. Well, next year there's a 3 gigahertz or a 4 gigahertz computer, and you might then claim that, wow, my algorithm is now twice as fast. Well, in reality, that's obviously not the case. It's just the hardware has gotten faster, but your computer has not. And so we really want to throw away things like multiples of 2 or multiples of 3 when it comes to describing how fast or how slow an algorithm is, and really just focus on n, or some factor thereof, some power thereof, as in the case of the sorts from last week. And recall that with the help of merge sort, we were able to do so much better than bubble sort and selection sort and even insertion sort. We got down to n log n. And again, recall that log n just generally refers to something that grows more slowly than n. So n log n thus far was good because it was less than n squared. But to achieve n log n with merge sort, what was sort of the basic germ of an idea that we had to leverage, that we also leveraged back in week 0? How did we tackle the sorting problem cleverly with merge sort? What was the key insight, perhaps? Anyone at all? So, OK, let's take a step back. Describe merge sort in your own words. How did it work? OK, we'll roll back to week 0. OK, yeah. OK. OK, good. So we divided the array of numbers into 2 pieces. We sorted each of those pieces, and then we merged them. And we've seen this idea before of taking a problem that's this big and chopping it up into a problem that's this big or this big. Recall the phone book example. Recall the self-counting algorithm from weeks ago. So merge sort was summarized by this pseudocode here. When you're given n elements, first do a sanity check. If n is less than 2, well, then don't do anything at all. Because if n is less than 2, then n is obviously 0 or 1. And so if it's either 0 or 1, there's nothing to sort. You're done. Your list is already trivially sorted. But otherwise, if you've got 2 or more elements, go ahead and divide them into 2 halves, left and right, sort each of those halves, and then merge the sorted halves. But the problem here is that at first glance, this kind of feels like we're punting. This is kind of a circular definition in that if I've asked you to sort these n elements and you're telling me, all right, fine, we'll sort those n over 2 and those n over 2 elements, then my next question is going to be, fine, how do you sort the n over 2 elements? But because of the structure of this program, because there is this base case, so to speak, this special case that says if n is less than some fixed value like 2, return immediately, don't respond with that same circular answer, this process, this cyclicity, will eventually end. If I ask you, sort these n elements, and you say, fine, sort these n over 2, then you say, fine, sort these n over 4, n over 8, n over 16, eventually you'll divide by a big enough number that you'll have just one element left, at which point you can say, here is a sorted single element. So then the brilliance of this algorithm appears to derive from the fact that once you have all of these individually sorted lists, all of which are of size 1, which seems to be useless, once you start merging them and merging them, you build up finally, as Rob did in the video, a finally sorted list. But this idea extends far beyond sorting. There's this idea embedded in this program known as recursion. The idea whereby you are a program, and to solve some problem, you call yourself. Or put in the context of programming languages, you are a function, and in order to solve a problem, you, the function, call yourself again and again and again. But you, the function, can't call yourself infinitely many times. Eventually, you have to bottom out, so to speak, and have some hard-coded base condition that says, at this point, stop calling yourself, so that the whole process finally does, in fact, stop. So what does this really mean to recurse? Well, let's see. If we could do a simple, trivial example with, say, 3 people with me up here on stage, if someone's comfortable. 1, come on up. 2 and 3. If you got 3 want to come up here. So if you want to stand right next to me here in a line, suppose that the problem at hand is very trivially count the number of people who are here. But frankly, I'm tired of all these counting examples. This is going to take me some time to 1, 2, and ... It's going to take forever. I'd rather just punt this problem altogether with the help of, what's your name?
Sarah.
Sarah, all right.
Kelly.
Kelly and Willie. Sarah, Kelly, and Willie. So right now, I have been asked the question by someone, how many people are up on this stage? And I have no idea. This is a really long list. And so instead, I'm going to do this trick. I'm just going to ask the person next to me to do most of the work. And once she is done doing most of the work, I'm just going to do the least amount of work possible and just add 1 to whatever her answer is. So here we go. I've been asked how many people are on stage. How many people are on stage to the left of you?
The left of me? 2.
Oh, OK, but don't cheat. So that's good. That's correct. But if we want to continue this logic, let's assume that you similarly want to punt this problem to the left of you. So rather than answer directly,
1.
go ahead and just pass the buck.
How many people are the left of you? How many people are the left
OK. So 0. So what now Willie's done is you've returned your answer this direction saying 0. Now what should you do?
1.
OK, so you're the 1. So you say, all right, I'm going to add 1 to whatever Willie's count was. So 1 plus 0, you're now 1. So your answer to the right is now
1. All right, mine would be 2.
good. So you're taking the previous answer of 1, adding the minimal amount of work you want to do, which is plus 1. You give me, now have 2, and you then hand me which value?
3. I mean, sorry, 2 because, sorry.
Good. Well, so we had 0 to the left, then we had 1, and then we had 2, and now you're handing me the number 2. And so I'm saying, OK, plus 1, 3. There's indeed 3 people standing next to me on this stage. So we could have obviously done this very linearly, very much in the obvious fashion. But what did we really do? We took a problem of size 3 initially. We then broke it down into a problem of size 2, then a problem of size 1. And then finally, the base case was really, there's no one there, at which point Willie returned effectively a hard-coded answer a couple times. And the second one was then bubbled up, bubbled up, bubbled up. And then by adding in this one additional 1, we've implemented this basic idea idea of recursion. Now, in this case, it didn't really solve a problem any more effectively than we've seen thus far. But think about the algorithms we've done on stage thus far. We had 8 pieces of paper on the chalkboard on video when Sean was looking for the number 7. And what did he really do? Well, he didn't do any kind of divide and conquer. He didn't do any kind of recursion. Rather, he just did this linear algorithm. But when we introduced the idea of sorted numbers on stage live last week, then we had this instinct of going to the middle, at which point we had a smaller list of size 4 or another list of size 4, and then we had the exact same problem. So we repeated. In other words, we recursed. So thank you very much to our 3 volunteers here for demonstrating recursion with us. Let's see if we can't make this now a little more concrete, solving a problem that, again, we could do pretty easily, but we'll use it as a stepping stone to implementing this basic idea. So if I want to compute the summation of a bunch of numbers, for instance, if you pass in the number 3, I want to give you the value of sigma 3. So the sum of 3 plus 2 plus 1 plus 0. I want to get back the answer 6. So we'll implement this sigma function, this summation function that, again, takes an input and then returns the summation of that number all the way down to 0. So we could do this pretty simply, right? We could do this with some kind of looping structure. So let me go ahead and get this started. So include standard io.h. Let me give myself int main to work with here. Let's save this as sigma.c. Then I'm going to go in here, and I'm going to declare an int n. And I'm going to do the following while the user does not cooperate. So while the user has not given me a positive number, let me go ahead and prompt them for n get int. And let me give them some instructions as to what to do. So printf positive integer, please. So just something relatively simple like this, so that by the time we hit line 13 and line 14, we now have a positive integer, presumably an n. Well, now let's do something with it. Let me go ahead and compute the summation. So int sum gets, let's say, sigma of n. So sigma is just summation, so I'm just writing it in the fancier way. So we'll just call it sigma there. So that's the sum, and now I'm going to print out the result. Printf of the answer, let's see, the sum is %d, new line, comma, sum. And then I'll return 0 for good measure. OK, so we've done everything that this program requires except the interesting part, which is to actually implement the sigma function. So let me go down here to the bottom, and let me declare a function sigma. It's got to take a variable that's of type integer. And what data type do I want to return, presumably, from sigma? OK, so int, because I just wanted to match my expectations on line 15. All right, so in here, let me go ahead and implement this in a pretty straightforward way. Let's go ahead and say int sum gets 0. And now I'm going to go have a little for loop here that's going to say something like this. So for int I gets 0, I is less than or equal to that number, I plus plus, sum equals plus equals I, and then I'm going to return sum. Could have implemented this in any number of ways. Could have used a while loop. Could have skipped using the sum variable if I really wanted to. But in short, we just have a function that if I didn't goof, could declare sum as 0. Then it iterates from 0 on up through the number. And on each iteration, it adds that current value to sum and then returns sum. Now, there's a slight optimization here. This is probably a wasted step, but so be it. That's fine for now. We're at least being thorough and going 0 all the way on up. All right, so not very hard and pretty straightforward. But it turns out that with the sigma function, we have the same opportunity as we did here on stage. On stage, we just counted how many people were next to me. But instead, if we wanted to count the number 3 plus the number 2 plus the number 1 on down to 0, we could similarly punt to a function that I'll instead describe as being recursive. So here, let's do a quick sanity check and make sure I didn't goof. I know there's at least one thing in this program that I did do wrong. When I hit enter, am I going to get any kind of yelling at me? OK, what am I going to be yelled about? Yeah, so I forgot the prototype. So I'm using a function called sigma on line 15, but it's not declared until line 22. So I'd best proactively go up here and declare a prototype. And I'll say int sigma takes an integer as its input, and that's it. It's implemented at the bottom. Or another way I could solve this. I could just move the function up there, which isn't bad, but at least when your programs start to get long, frankly, I think there's some value in just always having main at the top so that you and the reader can open the file and then immediately see what the program's doing without having to search through it looking for that main function. All right, so let's go down to my terminal window here. Try making sigma, make sigma. And I screwed up here too. Implicit declaration of function getInt means I've forgotten to do what else? OK, good. So apparently common mistake. So let's put this up here, CS50.h. And now let's go back to my terminal window. I'll clear the screen. And I'll rerun make sigma. Seems to have compiled. Let me now run sigma. I'll type in the number 3, and I indeed get 6. So not a rigorous check, but at least it seems to be working at first glance. But now let's rip it apart. And let's actually leverage this idea of recursion, again, in a very simple context so that in a few weeks' time, when we start exploring fancier data structures than arrays, we have another tool in the toolkit with which to manipulate those data structures, as we'll see. So this is the iterative approach, the loop-based approach. Let me instead now do this. Let me instead say that the summation of number on down to 0 is really the same thing as number plus sigma of number minus 1. In other words, just like on stage, I punted to each of the people next to me, and they in turn kept punting until we finally bottomed out at Willie, who had to return a hard-coded answer like 0. Here now, we're similarly punting to sigma, the same function as was originally called, but the key insight here is that we're not calling sigma identically. We're not passing in n. We're clearly passing in number minus 1. So a slightly smaller problem, Unfortunately, this isn't quite a solution yet. And before we fix what some might be jumping out as obvious at some of you, let me go ahead and rerun make. Seems to compile OK. Let me rerun sigma with 6. Whoops. Let me rerun sigma with 6. We've seen this before, albeit accidentally last time as well. Why did I get this cryptic segmentation fault? Yeah. So there's no base case. And so more specifically, what probably happened? This is a symptom of what behavior? Say a little louder. So it's an infinite loop, effectively. And the problem with infinite loops when they involve recursion in this case, a function calling itself, what happens every time you call a function? Well, think back to how we laid out the memory in a computer. We said that there's this chunk of memory called the stack that's at the bottom. And every time you call a function, a little more memory gets put on this so-called stack containing that function's local variables or parameters. So if sigma calls sigma, calls sigma, calls sigma, calls sigma, where does this story end? Well, it eventually overruns the total amount of memory that you have available to your computer. You overrun the segment that you're supposed to stay within, and you get this segmentation fault, core dumped. And what core dumped means is that I now have a file called core, which is a file containing zeros and ones that actually in the future will be diagnostically useful if it's not obvious to you where your bug is. You can actually do a bit of forensic analysis, so to speak, on this core dump file, which again is just a whole bunch of zeros and ones that essentially represents the state of your program in memory the moment it crashed in this way. So the fix here is that we can't just blindly return sigma, the number plus sigma of a slightly smaller problem. We need to have some kind of base case here. And what should the base case probably be? OK, so long as the number is positive, we should actually return this. Or put another way, if number is, say, less than or equal to 0, you know what? I'll just go ahead and return 0, much like Willie did. And else, I'm going to go ahead and return this. So it's not that much shorter than the iterative version that we whipped up first using a for loop. But notice that there's this sort of elegance to it, right? Instead of just returning some number and performing all this math and adding things up with local variables, you're instead just saying, OK, well, if this is a super easy problem, like the number is less than 0, let me just immediately return 0, right? We're not going to bother supporting negative numbers, so I'm just going to hard code the value of 0. But otherwise, to implement this idea of summing all of these numbers together, you can effectively take a small bite out of the problem, much like we did here on stage, then punt the rest of the problem to the next person. But in this case, the next person is just yourself. It's an identically named function. Just pass it a smaller and smaller and smaller problem each time. And even though we haven't quite formalized things in code here, this is exactly what was going on in week 0 with the phone book. This is exactly what was going on in past weeks with Sean and with our demonstrations of searching for numbers, is taking a problem and dividing it again and again. So in other words, there's a way now of translating this real world construct, this higher level construct of divide and conquer, and doing something again and again in code. So this is something we will see again over time. Now, as an aside, if you're new to recursion, you should at least understand now why this is funny. I'm going to go to google.com, and I'm going to search for some tips and tricks on recursion. Enter. Tell the person next to you if they weren't laughing just now. All right, so did you mean recursion? Did you mean there we go. OK, so now that's the rest of everyone. All right, so a little Easter egg embedded somewhere there in Google. As an aside, one of the links we put on the course's website for today is just this grid of various sorting algorithms, some of which we looked at last week. But what's nice about this visualization, as you try to wrap your mind around various things related to algorithms, know that you can very easily now start with different types of inputs. The inputs all reverse, the inputs mostly sorted, the inputs random, and so forth. So as you try to, again, distinguish these things in your mind, realize that this URL on the course's website on the lectures page might help you reason through some of those. All right, so today we finally get to solve this problem from a while back, which was that this swap function just didn't work. And what was the fundamental problem with this function swap, the goal of which was, again, to exchange a value here and here such that this happens? This didn't actually work. Why? Yeah? Exactly. The explanation for this bugginess simply was because when you call functions in C and those functions take arguments like a and b here, you are passing in copies of whatever value you're providing to that function. You are not providing the original values themselves. So we saw this in the context of buggy3.c, which looked a little something like this. Recall that we had x and y initialized to 1 and 2 respectively. We then printed out what they were. I then claimed that I was swapping them by calling swap of x comma y. But the problem was that the swapping worked, but only in the scope of the swap function itself. As soon as we hit line 40, those swapped values were thrown away. And so nothing in the original function, main, was actually changed at all. So if you think back then as to what this looks like in terms of our memory, if this left-hand side of the board represents, and I'll do my best for everyone to see this, if this left-hand side of the board represents, say, your RAM, and the stack is going to grow on up this way, and we call a function like main, and main has two local variables, x and y. Let's describe those as x here, and let's describe these as y here, and let's put in the values 1 and 2. So this here is main. And when main calls the swap function, the operating system gives the swap function its own swath of memory on the stack, its own frame on the stack, so to speak. It also allocates 32 bits for these ints. It happens to call them a and b, but that's totally arbitrary. It could have called them whatever it wants. But what happens when main calls swap is it takes this 1, puts a copy there, puts a copy there. There was one other local variable in swap, though, called what? Temp. So let me give myself another 32 bits here. And what did I do in this function? I said int temp gets a. So a has 1. So I did this when we last played with this example. Then a gets b. So b is 2. So now this becomes 2. And now b gets temp. So temp is 1. So now b becomes this. That's great. It worked. But then as soon as the function returns Swap's memory effectively disappears so that it can be reused by some other function in the future, and main is obviously completely unchanged. So we need a way of fundamentally solving this problem. And today we'll finally have a way of doing this whereby we can introduce something called a pointer. It turns out that we can solve this problem not by passing in copies of x and y, but instead by passing in what, do you think, to the swap function? Yeah, what about the address? Right? We haven't really talked about addresses in much detail, but if this blackboard represents my computer's memory, we could certainly start numbering the bytes in my RAM and say this is byte number 1, this is byte number 2, byte number 3, byte number 4, byte number ... 2 billion if I have 2 gigabytes of RAM. So we could certainly come up with some arbitrary numbering scheme for all the individual bytes in my computer's memory. So what if instead, when I call swap, rather than pass in copies of x and y, why don't I instead pass in the address of x here, the address of y here, essentially the postal address of x and y, because then swap, if he's informed of the address in memory of x and y, then swap, if we change him a little bit, he could potentially drive to that address, so to speak, x, and change the number there, then drive to the address of y, change the number there, even while not actually getting copies of those values himself. So even though we've talked about this as being main's memory and this as being swap's memory, the powerful and the dangerous part of C is that any function can touch memory anywhere in the computer. And this is powerful in that you can do very fancy things with computer programs in C. This is dangerous because you can also screw up very easily. In fact, one of the most common ways for programs these days to be exploited still is for a programmer not to realize that he or she is allowing a data to be written in a location in memory that wasn't intended. For instance, he or she declares an array of size 10, but then accidentally tries to put 11 bytes into that array of memory, and you start touching parts of memory that are no longer valid. Just to contextualize this, some of you might know that software often prompts you for serial numbers or registration keys, Photoshop and Word and programs like this. Well, there exist cracks, as some of you know, online, where you can run a little program and voila, no more request for a serial number. Well, how is that working? Well, in many cases, these things are simply finding in the computer's text segment, in the computer's actual zeros and ones, where is that function where the serial number is requested, and you overwrite that space. Or while the program is running, you can figure out where the key is actually stored using something called a debugger, and you can sort of crack software that way. So this isn't to say that this is our objective for the next couple of days, but it has very real-world ramifications. That one happens to involve theft of software, but there's also compromise of entire machines. In fact, when websites these days are exploited and compromised and data is leaked and passwords are stolen, this very often relates to poor management of one's memory, or in the case of databases, failure to anticipate adversarial input. So more on that in the weeks to come. But for now, just a sneak preview of the sort of damage that you can do by not quite understanding how things work underneath the hood. So let's go about understanding why this is broken with a tool that will become more useful, more and more useful as our programs get more complex. Thus far, when you've had a bug in your program, how have you gone about debugging it? What have your techniques been thus far, whether taught by your TF or just sort of self-taught? Printf, all right? So printf has probably been your friend in that if you want to see what's going on inside of your program, you just put printf here, printf here, printf here, then you run it, and you get a whole bunch of stuff on the screen that you can use to then deduce what is actually going wrong in your program. So printf tends to be a very powerful thing, but it's a very manual process, right? You have to put a printf here, and if you put it inside of a loop, you might get 100 lines of output that you then have to sift through. It's not a very user-friendly or interactive mechanism for debugging programs. But thankfully, there exist alternatives. There's a program, for instance, called GDB, the GNU Debugger, which is a little arcane in how you use it. It's a little complex. But frankly, this is one of those things where if you put in this week and next the extra hour to understand something like GDB, it will save you probably tens of hours in the long run. So with that, let me give you a teaser of how this thing works. I'm in my terminal window. Let me go ahead and compile this program, Buggy3. It's already up to date. Let me run it, just like we did a while back. And indeed, it's broken. But why is this? Maybe I screwed up the swap function. Maybe it's A and B. I'm not quite moving them around correctly. So let me go ahead and do this. Rather than just run Buggy3, let me instead run this program, GDB. And I'm going to tell it to run Buggy3. And I'm going to include a command line argument -tui. And we'll put this in a future problem set spec to remind. And now this black and white interface popped up that, again, is a little overwhelming at first because there's all this like warranty information down here. But at least there's something familiar. In the top of the window is my actual code. And if I scroll up here, let me scroll to the very top of my file. And indeed, there's buggy3.c. And notice at the bottom of this window, I have this GDB prompt. This is not the same as my normal John Harvard prompt. This is a prompt that's going to allow me to control GDB. GDB is a debugger. A debugger is a program that lets you walk through execution of your program line by line by line, along the way doing anything you want to the program, even calling functions, or looking, more importantly, at various variables values. So let's go ahead and do this. I'm going to go ahead and type in run at GDB's prompt. So notice at the bottom left of the screen, I've typed run, and I've hit enter. And what did that do? It literally ran my program. But I didn't actually see much go on here because I have not actually told the debugger to pause at a particular moment in time. So just typing run just kind of runs the program. I don't actually see anything. I can't manipulate it. So instead, let me do this. At this GDB prompt, let me instead type break, enter. That's not what I meant to type. Let's instead type break main. In other words, I want to set something called a breakpoint, which is kind of aptly named because it will break or pause execution of your program at that particular place. Main is the name of my function. Notice that GDB is pretty smart. It figured out that main happens to start roughly at line 18 of buggy3.c. And then notice here at top left, B+ is right next to line 18. That's reminding me that I have set a breakpoint at line 18. So this time when I type run, I'm going to run my program up until it hits that breakpoint. So the program will pause for me at line 18. Here we go, run. All right, so nothing appears to have happened. But notice at bottom left, starting program, buggy3, breakpoint 1 in main at buggy3.c, line 18. All right, so what can I do now? Well, notice I can start typing things like print, not printf, print x. And now that's strange. The $1 is just a curiosity. As we'll see, every time you print something, you get a new $sign value. That's so that you can refer back to previous values, just in case. But for now, what print is telling me is that the value of x at this point in the story is apparently 13514,032. What? Where did that even come from? So indeed, this is what we'll call a garbage value. And we've not talked about this yet, but the reason that you initialize variables is obviously so that they have some value that you want them to have. But the catch is, recall that you can declare variables like I did a moment ago in my Sigma example without actually giving them a value. Recall what I did over here in Sigma. I declared n, but what value did I give it? Well, none, because I knew that in the next few lines, getInt would take care of the problem of putting a value inside of n. But at this point in the story of line 11 and line 12 and line 13 and line 14, throughout those several lines, what is the value of n? Well, in C, you just don't know. It's generally some garbage value, some completely random number that's left over, essentially, from some previous function having been run. So as your program runs, recall that function gets function, function, function. All these frames get put on memory, and then those functions return. And so just like I suggested with the eraser, their memory is eventually reused. Well, it just so happens that this variable x in this program seems to have contained some garbage value like 13514,032 from some previous function. Not one that I wrote, could be something that comes effectively with the operating system, some function underneath the hood. So, OK, that's fine, but let's now advance to the next line. If I type next at my GDB prompt and then hit enter, notice that the highlighting moves down to line 19. But the logical implication is that line 18 has now finished executing. So if I, again, type print x, I should now see 1. And indeed, I do. Again, the $sign stuff is just a way of GDB reminding you what the history of prints are that you've done. So now let me go ahead and print out y. And indeed, y is some crazy value as well. But no big deal, because in line 19, we're about to assign it the value 2. So let me type next again. And now we're on the printf line. Let me do print x. Let me do print y. Frankly, I'm getting a little tired of printing this. Let me instead type display x and display y. And now every time I type a command in the future, I will be reminded of what's x and y, what's x and y, what's x and y. I can also, as an aside, type in info locals. Info is a special command. Locals means shows me the local variables. Just in case I forget, or this is a crazy complicated function that I or someone else wrote, info locals will just tell you what are all the local variables inside this function that you might care about if you want to poke around. Now, printf is about to execute. So let me go ahead and just type next. Let me go ahead, because we're in this environment, we're not actually seeing it execute down here. But notice it's getting a little mangled here. But notice it's kind of overwriting the screen there. So it's not a perfect program here. But that's OK, because I can always just poke around using print if I want. Let me type next again. And now here's the interesting part. At this point in the story, y is 2 and x is 1, as suggested here. And again, the reason this is automatically displaying now is because I use the command display x and display y. So the moment I type next, in theory, x and y should become swapped. Now, we already know that's not going to be the case, but we'll see in a moment how we can dive deeper to figure out why that's true. Next, and unfortunately, y is still 2 and x is still 1. And I can confirm as much, print x, print y. Indeed, no swapping has actually happened. So let's start this over. And it's clearly swap is broken. Let's instead type run again. Let me say, yes, I want to restart it from the beginning. Enter. Now I'm back up at line 18. Now notice x and y are garbage values again. Next, 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 next. If I get bored, I can also just type n for next. You can abbreviate it to the shortest possible sequence of characters. Swap is now broken. Let's dive in. So instead of typing next, now I'm going to type step, so that I'm stepping inside of this function so that I can walk through it. So I hit step and then enter. Notice that the highlighting jumps down lower in my program to line 36. Now, what are the local variables? Info locals. Nothing just yet because we've not gotten to that line. So let's go ahead and say next. OK, now we seem to have temp, print temp. Garbage value, right? I think so. How about print A? OK, print B, 1 and 2. So in a moment, as soon as I type next again, temp is going to take on a value of 1, hopefully, because temp is going to be assigned the value of A. So now let's do print A, print B, but now print temp, and it's indeed 1. Let me do next. Let me do next. I've finished the swap function. I'm still inside of it in line 40. So let me print A, print B, and I don't care what temp is. So it looks like swap is correct when it comes to swapping A and B. But if I now type next, I jump back to line 25. And of course, if I type in x and print y, they're still unchanged. So we haven't fixed the problem. But diagnostically now, perhaps, with this GDB program, we've at least gotten one step closer to understanding what's going wrong without having to litter our code by putting a printf here, printf here, printf here, and then running it again and again, trying to figure out what's going wrong. So I'm going to go ahead and just quit out of this altogether. With quit, it's going to then say quit anyway, yes. Now I'm back at my normal prompt, and I'm done using GDB. As an aside, you don't need to use this -TUI flag. In fact, if you omit it, you get essentially just the bottom half of the screen. If I then type break main and then run, I can still run my program. But what it will do is more textually just show me the current line, one at a time. So the -TUI textual user interface just shows you more of the program at once, which is probably a bit conceptually easier. But indeed, I can just do next, next, next. And I'm just going to see one line at a time. And if I really want to see what's going on, I can type list and see a whole bunch of neighboring lines. So there's a video that we've asked that you watch for problem set 3, in which Nate covers some of the intricacies of GDB. And this is one of those things, honestly, where some non-trivial percentage of you will never touch GDB. And that will be a bad thing, because literally you will end up spending more time later this semester chasing down bugs than you would if you put in that hour this week and next, just kind of learning to get comfortable with GDB. Printf was your friend. GDB should now be your friend. All right, any questions on GDB? And here's a quick list of some of the most powerful and useful commands. Yeah? Can you print a string? Absolutely. It doesn't have to just be integers. If a variable s is a string, just typing print s will show you what that string variable is. It will give you the address and the string itself. It will show you both. All right. And one last thing, just because these are good to know too. Backtrace and frame. Let me dive into this one last time. Same exact program with GDB. Let me go ahead and run the textual user interface version. Break main. Let me go ahead and run again. Here I am. Now let me go next, 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 step, enter. And now, suppose I'm now in swap deliberately, but I'm like, oh, damn, what was the value of x? I can't do x anymore. I can't do y because they're not in scope. They're not in context. But no problem. I can type backtrace. That shows me all of the functions that have executed up till this point in time. Notice that the one on the bottom, main, lines up with main being on the bottom of our picture here. The fact that swap is above it lines up with swap being above it in memory here. And if I want to get back to main temporarily, I can say frame, what number? So main is frame number 1. So I'm going to go ahead and say frame 1. Now I'm back in main, and I can print x and I can print y, but I can't print, I can't print a or b. But I can, if I say, OK, wait a minute, where was the swap? Let me go ahead and say frame 0. Now I'm back where I want to be. And as an aside, there's other commands too. Like if you're really getting bored typing next, 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 you can generally say things like next 10, and that will step through the next 10 lines. You can also write continue when you really get fed up with stepping through it. Continue will just run your program without interruption until it hits another breakpoint, whether in a loop or lower down in your program. So in this case, we continue to the end, and the program exited normally. This is just a fancy way, inferior process, just your program exited normally. All right, so more on that in the video and in debugging sessions to come. All right, so that was a lot. Let's take our 5-minute break here, and we'll return with structs and files. All right. So if you have dived into this week's pset already, you'll know that we use in the distribution code, the source code that we provide to you as a starting point, some new techniques. In particular, we introduced this new keyword called struct for structure so that we can create customized variables of sorts. We also introduced the notion of file I/O, file input and output. And this is so that we can save the state of your scramble board to a file on disk so that the teaching fellows and I can understand what's going on inside of your program without having to manually play dozens of games of Scramble. We can do this more automatedly. So this idea of a struct solves a fairly compelling problem. Suppose that we want to implement some program that somehow keeps track of information on students. And a student might have, for instance, an ID, a name, and a house at a place like Harvard. So these are 3 pieces of information we want to keep around. So let me go ahead and start writing a little program here. Include standard.io.h. Let me do include CS50.h. And then start my main function. I won't bother with any command line arguments. And here I want to have a student. So I'm going to say a student has a name. So I'm going to say string name. Then I'm going to say a student also has an ID. So int ID. And a student has a house. So I'm also going to say string house. And I'll order these a little more cleanly like this. OK, so now I have 3 variables with which to represent a student. So a student. And now I want to populate these values. So let me go ahead and say something like ID is going to get 1, 2, 3. Name is going to get quote unquote David. Let's say house is going to get quote unquote Mather. And then I'm going to do something arbitrarily like printf %s whose ID is %d lives in %s period. And now what do I want to plug in here? One after the other? So name, ID, house, semicolon, return 0. OK, so unless I screwed up somewhere here, I think we have a pretty good program that stores 1 student. All right, of course, this is not all that interesting. What if I want to have 2 students? All right, that's no big deal. I can support 2 people. So let me go ahead and highlight this, go down here. And I can say ID is 456 for someone like Rob, who lives in Kirkland. OK, wait, but I can't call these the same thing. And OK, looks like I'm going to have to copy this. So let me say that these will be David's variables. And let me get some copies of these for Rob. OK, we'll call these Rob's. All right, but this isn't going to work now because I have OK, wait, let's change me to ID1, name1, and house1. Rob will be 2, 2. OK, got to change this here, 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 here. OK. OK, wait, what about Tommy? So let's do this again. All right, so obviously, this is, if you still think this is like a good way of doing this, it's not, right? So copy, paste, bad. But so we solved this kind of like a week ago. What was our solution when we wanted to have multiple instances of the same data type? All right, so an array. So let me try to clean this up. Let me make some room for myself at the top. And let me instead do this here. So we'll just call these people. And instead, I'm going to say int IDs. And I'm going to support 3 of us for now. I'm going to say string names. And I'll support 3 of us. And then I'm going to say string houses. And I'm going to support 3 of us. So now in here, instead of David getting his own local variables, we can get rid of those. That feels good that we're cleaning this up. I can then say David is going to be bracket 0. And names bracket 0. And houses bracket 0. And then Rob, we can similarly save on this. Let's put this down here. So he's going to arbitrarily be IDs bracket 1. He's going to be names bracket 1. And then lastly, houses bracket 1. OK, so still a little tedious. And now I have to figure this out. So let's see, names 0, ID 0, houses 0. And oops, let's pluralize this. OK, IDs, IDs, IDs. All right. Oh, and again, I'm doing it. So again, I'm already resorting to copy paste again. So odds are there's another solution here. I can probably clean this up further with like a loop or something like that. So in short, it's a little better, but still feels like I'm resorting to copy paste. But even this, I claim, is not really fundamentally the right solution. Because what if sometime we decide, you know what, we really should have been storing email addresses for David and Rob and everyone else in this program. We should also store phone numbers. We should also store like emergency contact number. We have all these pieces of data that we want to store. So how do you go about doing that? Well, you declare another array at the top, and then you manually add an email address bracket 0, email address bracket 1 for David and Rob, and so forth. But there's really just an assumption underlying this design that I am sort of using the honor system to know that bracket I in each of these several arrays just so happens to refer to the same person. So bracket 0 in IDs is number 1, 2, 3. And I'm just going to assume that names bracket 0 is the same person's name, and houses bracket 0 is the same person's house, and so forth, for all of the various arrays that I create. But notice that there's no sort of fundamental linkage among those 3 pieces of information, ID, name, and house, even though the entity we're trying to model in this program is not arrays, right? Arrays are just this programmatic way of doing this. What we really want to model in our program is a person like David, a person like Rob, inside of which, or encapsulating, is a name, an ID, and a house. So can we somehow express this idea of encapsulation, whereby a person has an ID, a name, and a house, and not resort to really this hack whereby we just sort of trust that bracket something refers to the same human entity in each of these disparate arrays? Well, we can actually do this. Let me actually go above main for now, and let me create my own data type for really the first time. We use this technique in Scramble, but here I'm going to go ahead and create a data type. And you know what? I'm going to call it student or person, and I'm going to use typedef for define a type. I'm going to say that this is a structure, and then this structure is going to be of type student, we'll say, even though it's a little dated now for me. So we'll say int ID, we'll say string name, then we'll say string house. So now, by the end of these few lines of code, I have just taught Clang that there exists a data type besides ints, besides strings, besides doubles, besides floats. As of this moment in time, line 11, there is now a new data type called student. And now I can declare a student variable anywhere I want. So let me scroll down here to people. Now I can get rid of this. And I can go back down to David here. And you know what? For David, I can actually say that David, we can literally name myself after, name the variable after myself, is going to be of type student. So this might look a little weird, but this isn't all that different from declaring something as an int or a string or a float. It just so happens to be called student now. And if I want to put something inside of this structure, I now have to use a new piece of syntax, but it's pretty straightforward. David.id gets 1, 2, 3. David.name gets DAVID in capital D. And David.house gets quote unquote Mather. And now I can get rid of this stuff here. So notice we've now kind of redesigned our program in really a much better way in that now our program mirrors the real world. There's a real world notion of a person or a student. Here we have now a C version of a person, or more specifically a student. Inside of that person is these relevant characteristics, ID, name, and house. So Rob essentially becomes the same thing down here. So student Rob, and now Rob.id gets 4, 5, 6. Rob.name gets quote unquote Rob. So the fact that the variable is called Rob is sort of meaningless. We could have called it X or Y or Z. We just named it Rob just to be sort of semantically consistent. But really the name is inside of that field itself. So now I have this. Now this too doesn't feel like the best design in that I've hard-coded David, I've hard-coded Rob, and I still have to resort to some copy and paste every time I want new variables. Moreover, I have to apparently give each of these variables a name, even though I'd much rather just describe these variables more generically as students. So now we can merge the ideas that have been working well for us and instead say, all right, you know what, give me a variable called students, and let's have it be of size 3. So now I can refine this further, get rid of the manually declared David, and I can instead say something like students bracket 0 here. I can then say students bracket 0 here, students bracket 0 here, and so forth. And I can go around and clean that up for Rob. I could also go about now maybe adding a loop and using getString and getInt to actually get these values from the user. I could go about adding a constant, because this is generally bad practice to hard code some arbitrary number like 3 right here, and then just remember that you should put no more than 3 students in it. Probably be better to use sharp define at the top of my file and factor that out. So indeed, let me go ahead and generalize this. Let me open up an example that's among today's examples in advance, structs1. This is a more complete program that uses sharp define up here and says we're going to have 3 students by default. Here I'm declaring a class worth of students, so a classroom of students. And now I'm using a loop just to make the code a little more elegant, populate the class with the user's input. So iterate from I equals 0 on up to students, which is 3. And then I just prompt the user in this version, what's the student's ID? And I get it with getInt. What's the student's name? And then I get it with getString. What's the student's house? I get it with getString. And then at the bottom here, I just decided to change how I'm printing these out and to actually use a loop. And who am I printing? Well, according to the comment, I'm printing anyone in Mather, and that's it. So Rob and Tommy and so forth, or actually Tommy's in Mather. Tommy and David would be printed in this case. But how is this working? Well, we haven't seen this function before. But take a guess as to what this does. Compares strings. Now, it's a little non-obvious how it compares strings, because it turns out if it returns 0, that means the strings are equal. If it returns a -1, that means one comes alphabetically before the other. And if it returns +1, that means the other word comes alphabetically before the other. And you can look online or at the man page to see exactly which way is which. But all this is now doing is it's saying if the ith person's house is equal to quote unquote Mather, then go ahead and print out so-and-so is in Mather. But here's something we haven't seen before, and we'll come back to this. I don't recall ever having to do this in any of my programs. Free is apparently referring to memory, freeing memory. But what memory am I apparently freeing in this loop at the bottom of this program? It looks like I'm freeing a person's name and a person's house, but why is that? Well, it turns out all these weeks that you've been using getString, we've kind of been introducing a bug into every one of your programs. GetString, by design, allocates memory so that it can return to you a string like DAVID or ROB, and you can then do whatever you want with that string in your program because we've reserved memory for you. The problem is all this time, every time you call getString, we, the authors of getString, have been asking the operating system, give us a bit of RAM for this string. Give us a bit of RAM for this next string. Give us some more RAM for this next string. What you, the programmer, have never been doing is giving us that memory back. So for these several weeks, all of the programs you've written have had what's called a memory leak, whereby they keep using more and more memory every time you call getString. And that's fine. We deliberately do that in the first weeks because it's not that interesting to have to worry about where the string is coming from. All you want is the word ROB to come back when the user types it in. But moving forward, we now have to start getting more sophisticated about this. Anytime we allocate memory, we better eventually hand it back. Otherwise, in the real world on your Mac or PC, you might have occasionally experienced symptoms where your computer is just sort of grinding to a halt eventually, or stupid spinning beach ball is just occupying the computer's entire attention and you can't do things. Now, that can be explained by any number of bugs, but among those possible bugs are things called memory leaks, whereby someone who wrote that piece of software you're using didn't remember to free memory that he or she asked the operating system for, not using getString, because that's a CS50 thing, but using similar functions that ask the operating system for memory. If you or they screw up and never actually return that memory, a symptom of that can be that a program slows and slows and slows down unless you remember to call free. So we'll come back to when and why you would call free, but let's go ahead just for good measure and try running this particular program. This was called structs1. Enter. Let me go ahead and run structs run. 1, 2, 3, David, Mather, 4, 5, 6, Rob, Kirkland, 7, 8, 9, Tommy, Mather, and we see David's in Mather, Tommy's in Mather. So this is just a little sanity check that the program is working. Now, unfortunately, this program's kind of a little frustrating in that I just did all that work. I typed in 9 different strings, hit enter, was told who was in Mather, yet obviously I knew who was in Mather already because I typed it. It would be at least nice if this program's more like a database and it actually remembers what I have typed in. So I never again have to input these student records. Maybe it's sort of like a registrarial system. Well, we can do this using this technique known as file I/O. So a file input and output, a very generic way of saying anytime you want to read files or write files, you can do this with a certain set of functions. Let me go ahead and open this example, structs2.c, which is almost identical, but let's see what it now does. At the top of the file, I declare a class of students. I then populate the class with the user's input. So those lines of code are exactly like before. Then if I scroll down here, I print everyone who's in Mather, arbitrarily like before. But this is an interesting new feature. These lines of code are new, and they introduce something here, file, all caps, and it has a star in here as well. Let me move this over here, a star over here as well. This function we haven't seen before, fopen, but it just means file open. So let's just skim through these, and this is something we'll come back to in future p-sets. But this line here essentially opens a file called database, and it specifically opens it in such a way that it can do what to it? Write. So W in quote unquote here just means it's telling the operating system, open this file in such a way that I can write to it. I don't want to read it. I don't want to just look at it. I want to change it and add stuff potentially to it. And the file is going to be called database. This could be called anything. This could be database.txt. This could be .db. This could be a word like foo. But I just arbitrarily chose to name the file database. This is a little sanity check that we'll come back to in great detail over time. If fp, for file pointer, does not equal null, that means all is well. So long story short, functions like fopen sometimes fail. Maybe the file doesn't exist. Maybe you're out of disk space. Maybe you don't have permission to that folder. So if fopen returns null, something bad happened. So conversely, if fopen does not return null, all is well, and I can start writing to this file. So here's a new trick. This is just a for loop that's iterating over each of my students. And this looks so similar to what we've done before, but this function is a cousin of printf called fprintf for file printf. And notice it's different in only 2 ways. One, it starts with f instead of p, but then its first argument is apparently what? It's a file, right? This thing called fp, which will eventually tease apart what a file pointer is. But for now, fp simply represents the file that I have opened. So fprintf here is saying print this user's ID to the file, not to the screen. Print the user's name to the file, not to the screen. The house to the file, not to the screen. And then down here, obviously, close the file. And then down here, free the memory. So the only difference between this version 2 and version 1 is the introduction of fopen and this all caps file with a star, and this notion of fprintf. So let's see what the end result is. Let me go into my terminal window. Let me rerun struct2, enter. Looks like all is well. Let's rerun struct2. 1, 2, 3, David, Mather, 4, 5, 6, Rob, Kirkland, 7, 8, 9, Tommy, Mather, enter. Looks like it behaved the same. But if I now do ls, notice what file is in here among all my code, database. So let's open that, gedit of database, and look at that. It's not the sexiest of file formats. It really is just one piece of data, line per line per line per line. But those of you who use Excel or CSV files, comma-separated values, I could certainly have used fprintf to instead maybe do something like this, so that I could actually create the equivalent of an Excel file by just separating things with commas, not just new lines. So in this case, if I had instead used commas instead of new lines, I could literally open this database file in Excel if I instead made it look like this. So in short, now that we have the power to write to files, we can now start persisting data, keeping it around on disk so that we can keep information around again and again. Notice a couple of other things that are now a bit more familiar. At the top of the C file, we have a typedef, because we wanted to create a data type that represents a word. So this type is called word, and inside of this structure, it's a little fancier now. Why is a word made up of apparently an array? Well, what is a word, just intuitively? It's just an array of characters. It's a sequence of characters back to back to back. So letters in all caps happens to be, we arbitrarily say, the maximum length of any word in the dictionary that we're using for Scramble. Why do I have a +1? The null character. Recall when we did the little bananagrams example, we needed a special value at the end of the word in order to keep track of where words actually ended. And as the problem set specification says, here we're associating with a given word a Boolean value, a flag, so to speak, true or false. Have you found this word already? Because we realize, you know what, we really need a way of remembering not only what a word is in Scramble, but whether or not you, the human, have found it, so that if you do find the word the, you can't just type the, enter, and get 3 points, 3 points, 3 points, 3 points. We want to be able to blacklist that word by setting a bool to true if you've already found it. And so that's why we encapsulated it in this structure. Now down here in Scramble, there's this other struct called dictionary. Absent here is the word typedef, because in this case, we needed to encapsulate the idea of a dictionary. And a dictionary contains a whole bunch of words, as implied by this array. And how many of those words are there? Well, whatever this variable called size says. But we just need one dictionary. We don't need a data type called dictionary. We just need one of them. So it turns out in C that if you don't say typedef, you just say struct. Then inside the curly braces, you put your variables. Then you put the name. This is declaring one variable called dictionary that looks like this. By contrast, these lines are creating a reusable data structure called word that you can create multiple copies of, just like we created multiple copies of students. So what does this ultimately allow us to do? Well, let me go back into, let's say, a simpler example from simpler times. And let me open up, let's say, compare1.c. So the problem here at hand is to actually peel back the layer of a string and start taking off these training wheels, because it turns out that a string all this time is, as we promised in week 1, really just a nickname, a synonym from the CS50 library for something that looks a little more cryptic, char star. And we've seen the star before. We saw it in the context of files. Let's now see why we've been hiding this detail for some time now. So here's a file called compare1.c, and it apparently asks the user for 2 strings, s and t. And then it tries to compare those strings for equality in line 26. And if they're equal, it says you type the same thing. And if they're not equal, it says you typed different things. Well, let me go ahead and run this program. So let me go into my source directory, make compare1. OK, compiled OK. Let me run compare1. I'll zoom in, enter, say something. Hello. So I'll say something again. Hello. I definitely didn't type different things. Let me try this again. So bye. Definitely not different. So what's going on here? Well, what is really being compared in line 26? Yeah, so it turns out that a string data type is kind of a white lie. A string is a char star. But what is a char star? A char star, as they say, is a pointer. And a pointer is effectively an address, some location in memory. And if you happen to have typed in a word like hello, recall from past discussions of strings, this is like the word hello, H-E-L-L, nope, H-E-L-L-O. Remember that a word like hello can be represented as an array of characters, like this, and then with a special character at the end called the null character, as the backslash denotes. So what is actually a string? Well, notice that this is multiple chunks of memory. And in fact, the end of it is only known once you look through the whole string, looking for this special null character. But if this is a chunk of memory from my computer's memory, let's arbitrarily say that this string just got lucky and it got placed at the very beginning of my computer's RAM. So this is byte number 0, 1, 2, 3, 4, 5, 6, ... So when I say something like get string, and I do string s gets get string, what's really being returned for these past several weeks, what's really being stored in s is not this string per se, but in this case, what's being stored is the number 0. Because what getString actually does is it doesn't physically return a string. That doesn't even really make conceptual sense. What it does return is a number. That number is the address of hello in memory. And string s then, if we peel back this layer, well, string doesn't really exist. It's only a simplification in the CS50 library. This really is something called char star. Now, char makes sense because what's a word like hello? Well, it's a series of chars, a series of characters. Char star means the address of a character. So what does it mean to return a string? Well, you know, a nice sort of a simple way of returning a string is rather than try to figure out how I return to you 5 or 6 different bytes, let me just return to you the address of which byte? The first one. In other words, let me give you the address of a character in memory. That's what char star represents, the address of one single character in memory. Call that variable s, store in s that particular address, which I arbitrarily said is 0, just to keep things simple, but in reality it's generally a bigger number. So wait a minute, if you're only giving me the address of the first character, how do I know what the address of the second character, the third, the fourth, and the fifth? You only know where the end of a string is by way of this handy trick. So when you use something like printf, what printf literally takes as its argument, recall that we use this %s placeholder, and then you pass in the variable that's storing a string. What you're really passing is the address of the first character of that string. Printf then uses a for loop or a while loop upon receiving that address, for instance, 0. So let me do this now. So printf, quote unquote, %s, new line, comma, s, double quote, semicolon. So when I call printf, %s new line, comma s, what I'm really providing printf with is the address of the first character in s, which in this arbitrary case is h. How does printf know what exactly to display on the screen? Well, the person who implemented printf implemented a while loop or a for loop that says, does this character equal the special null character? If not, print it. How about this one? If not, print it, print it, print it, print it. Oh, this one's special. Stop printing and return to the user. And that's literally all that's been happening underneath the hood. And that's kind of a lot to digest in the first day of a class. But for now, it's really just the building block of understanding everything that's been going on inside of our computer's memory. And eventually, we'll tease this apart with a little help from one of our friends at Stanford. Professor Nick Parlante at Stanford has done this wonderful video sequence from all sorts of different languages that introduce this little claymation character, Binky. The voice you're about to hear in just a few seconds sneak preview is that of a Stanford professor. You're getting only 5 or 6 seconds of this right now, but this is the note on which we'll conclude today and begin on Wednesday. I give you pointer fun with Binky, the preview.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody!
We will see you on Wednesday.